Is Earth's magnetic field about to flip? That's the big question that a lot of people have on their minds, and there is quite a bit of supporting evidence for that to occur in the near future. But there's also a lot of evidence showing that that may not happen and may not happen for a while. And this is based on Earth's magnetic field strength and its variations across time. So in this video, we are going to look at the available research on Earth's magnetic field strength and how it's a crucial, important ingredient for whether a geomagnetic excursion or reversal occurs. We'll also be looking at Earth's magnetic field in general and its spatiotemporal variations so we can better understand the chaotic system that is Earth's magnetic field. Hi everyone, welcome back to the channel. If you're new here, my name is Stefan Burns. I'm a geophysicist, and my background for reference is that I went to University of Davis and received a Bachelor of Science in Geology, and then I entered into the workforce as a geophysicist before venturing off into the whole YouTube realm as a citizen scientist. And in general, what I've noticed is that around this pole shift topic, this pole flip topic, there's a lack of good journalism and information dissemination. So I've read through a bunch of research papers on this. I have formal education on this topic. And so we're going to examine all this information and more and look at it very humbly and come to our best understanding as to what Earth's magnetic field has done in the past, where it is right now, and where it may go in the near future. We'll begin by looking at our total magnetic field intensity map for the globe. This is for 2020. It'll be updated in 2025. They update them every 5 years. So we have the magnetic intensity across the globe with this map. We see here our polar regions have higher intensity, and there in the Atlantic region near and over South America, we have a field area of lower intensity. We have our scale bar down here, measured in nanotesla. We see it goes up to 67,000 or so, goes down to about 23,000. And so the intensity low for the globe is in the South Atlantic Anomaly at about 23,000 nanotesla in this region here, right in the Brazil area. And then our intensity high for the world, for Earth's magnetic field strength, is near the south magnetic pole at about 67,000 nanotesla, and you see that location here. So this is in general the magnetic strength across the globe as measured at the surface. And I like this map here because it doesn't over accentuate any single color, which makes you think that a certain area or anomaly is bigger or more important than it should be otherwise. The color scale really matters when you look at this type of data. And this is just a simple graphic going from red to blue. So we do see this very big magnetic low, the South Atlantic Anomaly, which is the key to understanding whether we are in a geomagnetic excursion or reversal. We'll talk about this a lot more later in the video, but it's not the only feature. We have this double flux lobe in the North Pole, and then we have the South Pole, which has the strongest magnetic field strength. And in general, you see that the magnetic field strength is stronger in the poles and then goes and weakens at the equator and then strengthens again at the southern pole. The reason why is because the magnetic fields are strongest where they are vertical, and then as they go out around the globe, the horizontal field dominates. And at the equatorial regions, we have a ring current that circles, which is oppositional to Earth's static magnetic field. So it also reduces the field strength as a result. When that ring current gets enhanced during a geomagnetic storm, for example, the field strength drops even more. So these are some of the reasons why we have variations in Earth's magnetic field as measured at the surface, also across time. But this feature right here is associated with the geodynamo process, which is still very mysterious. It's very chaotic. We really don't understand geodynamos that well. We have a lot of ways to model them based on different inputs, but those models are always changing and evolving. And so we are using our best available data from satellites to map the core mantle boundary and to see these different regions of flux coming up from the core to try to understand the evolution of this South Atlantic anomaly and also the evolution of other flux lobes that have emerged from the Earth across time. We'll look at that. We have magnetic high anomalies in Hawaii, in Western Europe, in the Middle East, in Mesoamerica, just in the recent past. So there's a lot of new data coming out in our most recent 2,000 years of history showing a very complex dynamic magnetic field and variations, very large variations in magnetic field strength, even in just the past 1,000 years. So the South Atlantic Anomaly exists now, but there also used to be these really big anomalies in these areas here. We'll look at that. They don't exist now. So this shows that these secular variations and these big swings in magnetic field strength, either up or down, can occur on a century time scale and then go away. And so there's a lot to talk about in this video. Let's get into it. We'll expand a lot more on some of that content that I lightly talked about on that last slide. But to start, let's look at some basic facts going back to our ability to even measure the strength of a magnetic field. We used to only have compasses that would tell us the direction of a magnetic pole. And then eventually we developed an ability to measure the magnetic field relative to a certain location. This is a relative intensity measurement. And then in 1833, Gauss developed the ability to measure Earth's magnetic field strength or any magnetic field in terms of absolute SI international units. So standard international units. And so this has revolutionized our ability to measure Earth's magnetic field, the intensity, and that started in about 1840. We started to get a lot of widespread absolute intensity measurements of Earth's magnetic field. And what we've seen is that Earth's magnetic field strength has dropped by about 5% per century since 1840. So if we go 200 years, that's about 10%. There's a little bit of wiggle room there. Some people say 10, some people say about 12%. But in general, going back to the first absolute intensity measurements of Earth's magnetic field back in the 1840s and then going on, Earth's magnetic field strength has dropped by about 10%. So you hear claims out there of 20%, 30%, and this is widespread because people just say the same thing that someone else says, and it just eventually disseminates out. But going back to Gauss, who developed the ability for us to even measure this, it's about 10% in 2 centuries. Now, the axial dipole drop per year is approximately 12.5 nanotesla. So you calculate that, it comes out to about 5%. And that will slowly increase though as the strength continues to drop, if it does. And this dipole field strength has been decreasing at this rate of about 12.5, 15 nanotesla. That's the research range that people have identified since about 750 CE. Common Era, also 750 AD. So the Middle Ages. The current magnetic field intensity maximum, as I said earlier, is 67,000 nanotesla near the South Magnetic Pole, and the intensity minimum is about 23,000 nanotesla in the South Atlantic Anomaly. So if you hear values that are much different than that, like it's 10,000 nanotesla or it's 80,000 nanotesla, that's not right, because these are the current maxima and minima that we have very well established. We now have satellites that orbit the Earth every single day, taking hundreds of magnetic field measurements and across very tight spacing. So we know Earth's magnetic field strength very well at this moment in time. And we have since about 1840, because after 1833, when Gauss developed this ability, there were already a lot of people out there measuring Earth's magnetic field strength, but in a relative way. They would have a reference location, and then they would go on a ship and they would take their cruise, maybe to the Caribbean or something, get all their measurements, and it was referenced to, let's say, Paris. But once the absolute intensity measurement was developed, a whole bunch of observatories sprung up around Europe and then also around the world like we have now. And so this is a very well-defined drop in Earth's magnetic field strength dominated by the axial dipole moment. So the changes to Earth's magnetic field strength are attributable to geodynamo changes, a chaotic process we do not understand. And this is because we don't even know if it is a geodynamo that's powering Earth's magnetic field. We think it is. There's a tremendous amount of evidence supporting that, but there are other theories out there. There's georeactor theory. We just know in general that inside Earth's interior, there's a static magnetic field being generated, which requires the movement of charge. because if you have a movement of charge carriers or an electric current, you generate a magnetic field. And so we can take the magnetic field strength that we know, we can calculate its attenuation through geologic rock in the mantle and come up with a field strength value at the core and then work backwards from there. We measure its changes across time using ground observatories, using satellites, using archaeointensity data, using paleomagnetic intensity data. And so we can look at all this indirectly, but we really don't know what's happening in the core. We think it's a geodynamo. It probably is a geodynamo. It's a very chaotic process that we're just now beginning to understand as computation power increases and our models can become better and better. Understanding secular variations of Earth's magnetic field is the key to understanding its future evolution. And also, what are the critical conditions required to undergo geomagnetic excursion or reversal? So there are a few different things that need to happen, it seems, for a geomagnetic excursion or a reversal to occur, where the poles flip. An excursion has the poles flip, but then it aborts and it goes back to its polarity that it had, and a reversal is a complete flip. The last geomagnetic reversal occurred back in about 780,000 years ago, and we've been in that polarity regime since. It's been pretty long compared to the average, but there's really no set rhythm for geomagnetic reversals. If you look at the record, it varies wildly across time. Millions of years, there's a period that lasted like 100 million years where the polarity didn't change at all. The last big excursion that we had was the Lechamp excursion about 41,000 years ago. We've had tiny excursions since, but the Lechamp excursion was nearly a full reversal that aborted and then went back. As we look back, the resolution gets lower, but in our near recent past, just in the past 2 decades, we've really undergone a lot of dedicated effort to measure Earth's magnetic field strength in various locations to a much higher resolution. And so now we're seeing some of these secular variations of Earth's magnetic field strength really come out, and it's changing the paradigm in our understanding of Earth's magnetic field, showing that Earth's magnetic field undergoes much more chaotic processes than we thought. It's much more dynamic than we thought. It doesn't just kind of stay the same and then go through an excursion and then stay the same for a while. It's always having these flux lobes push and pull out of it. So the South Atlantic Anomaly is the big area of reverse flux right now on our globe. But in the past, we had huge areas of flux, positive flux, like I said, with Hawaii, with Western Europe, with Levant Basin, with Mesoamerica. So we'll look at all that. But these are the known facts for Earth's magnetic field. These are well established, and all the links to research papers are in the video description. Here we have our magnetic field total intensity map going from 1840 to 1990. And if you look in the equatorial region, you'll see that magnetic flux change of the South Atlantic Anomaly. It spreads and grows. You also will see some changes up in the northern hemisphere with the 2 polar flux lobes, and also just in general a shifting of the contour lines. Here we have the South Atlantic Anomaly. We see how it will grow and expand across time. You also will see some changes in the northern hemisphere. This flux lobe over Canada gets smaller, reduces in strength, while the Siberian flux lobe gets bigger and increases in strength. So this is showing the evolution of Earth's north magnetic pole and the South Atlantic Anomaly. Here we have our horizontal intensity map for the same time frame, and the secular variations are not as obvious here as with the total intensity map, but we do see starting around 1900 this region of horizontal intensity form off the southern coast of Africa, and then it pushes towards South America, and this is connected to the South Atlantic Anomaly. The main thing you'll see in this vertical intensity map over time is the reduction of the Canadian flux lobe here and the growth of the Siberian flux lobe. So the north magnetic pole bifurcates into 2, and as the Canadian one has gone weaker, the Siberian one's gone stronger, pulling north magnetic pole towards that location over Siberia. Those maps show the spatial temporal evolution of Earth's magnetic field across time from 1840 to 1990 based on absolute intensity measurements. Now, one of the downfalls of that model, and just in general with our understanding of Earth's magnetic field, is that we didn't collect that many absolute intensity measurements for the southern hemisphere until just recently. First off, there's not too much landmass in the southern hemisphere. Most of it is ocean, so it's hard to collect surface measurements over the ocean permanently with a permanent observatory. And B, most of the absolute intensity measurements were collected in Europe and then America, and very few were done in Africa over time, and very few were done in South America and then Australia. So there is a deficit of absolute intensity measurements for the southern hemisphere until just recently. Now that we have satellites and everything, we have permanent observatories across the world. But that is an important region to have those absolute intensity measurements in if we really want to understand how the South Atlantic Anomaly has been evolving. And there are various research papers that show that when you add or subtract measurements from that region, the South Atlantic Anomaly can appear or it can disappear. And so it's very much based on the data that we have, and there's just a deficit of data in the Southern Hemisphere in general. It's very important to be aware of that. And that's with the absolute intensity measurements. That's also true in general with archaeointensity data. And so here we have Earth's magnetic field across two different time scales. So we can get a better sense of its field strength across time. We have here going to the present day there, 2000 AD, let's say. And then we have going all the way back to 12,000 BC. So this is 14,000 years ago. Now down here we have about 800,000 years of magnetic field strength, 800, 900,000 if you go to there. And so we see that Earth's magnetic field strength for the past 14,000 years has undergone some variations, but back here, 12,000 BCE, 10,000 BCE, 8,000 BCE, this general range there, Earth's magnetic field strength was quite a bit lower than it is now. This is our current value. Now what we're measuring here is the dipole moment, or the virtual axial dipole moment. So this isn't measured in nanotesla, it's a different way to measure this. But it in general still shows the same relative changes. And so we see that back in the past, Earth's magnetic field strength was typically weaker than what we have now. There were periods that were stronger here, like 7,000 BCE. But then we took a dip here, 4,000 BCE. That's below and for an extended period of time. And then we recently just came off of a high. So we had a lot of magnetic increases over the past 1,000 years or so. 2,000 years, we had this in general increasing trend, and now Earth's magnetic field strength has been dropping from that. And so that's one reason why Earth's magnetic field strength has been dropping, because it reached a local maximum, which if we look here, we see it's quite notable. Here's the same line, 7.74, plotted down below. And so we see that Earth's magnetic field strength right now, historically, across about 900,000 years, is very strong. Here's the modern day here, and we see that Earth's magnetic field strength in general is below this line. And then going back way back in time, right after the reversal, we see that there are some periods where it is stronger, but in general, Earth's magnetic field strength is actually quite strong. What we also notice is that Earth's magnetic field strength has to get quite low for an excursion to happen. So here's a reversal. The field strength goes extremely low during a reversal. During an excursion, it goes quite low as well, but not as low. So the field strength drops, the axial dipole disappears or severely weakens, and the other higher order parts of Earth's magnetic field emerge, the quadrupole, the octupole, and other things, but then eventually the axial dipole reemerges and re-strengthens. And so we see after this reversal, the magnetic field strength actually got quite strong. Same here, after this excursion, it got quite strong again. And so here after these three excursions, it shot back up. And so we are just now coming off on geologic time. On geologic time, we're just coming off of the Lechamp excursion 41,000 years ago. And so Earth's magnetic field strength strengthened dramatically after that. And so it's highly likely that we're just settling back to a more normal area or regime of Earth's magnetic field strength. We've been in a regime of very high, very strong magnetic field for about 2,000 years now. And so these changes that we're seeing in Earth's magnetic field really could just be a return to normal, and we'll explore that more. Here's a similar graphic. This is showing 100,000 years of magnetic field intensity evolution across time. 0 is the present day. Here's the Lechamp excursion. It pops right out when you look at this. We see just how much the field strength dropped. Now, we have a few different models that they're showing here. All of them are in fairly close agreement, though they do deviate around the Lechamp excursion. But in general, you'll see that Earth's magnetic field strength in this zone there is quite a bit higher than in general what happened. So we do have a region here which is kind of nice and high, around 90,000 years ago to about 80,000 years ago. But then there was this dip here around 62, 63,000 years ago. Then we hit this kind of this top before descending into the Lechamp. But now we've had this broad plateau. We didn't have this super rapid increase like we saw right before the Lechamp excursion. Of course, this right there is about 10,000 years. Remember, that's not 10 years. That's like 10,000 years of time before the Lechamp excursion occurred. But in general, Earth's magnetic field strength is quite high right now. So when you put it into the geologic context, nothing's out of the ordinary as it relates to Earth's magnetic field strength. And let's go back even further. Here we have paleointensity data going back 160 million years, published in Nature. And so we see that there are quite a lot of gaps here. We need to do a lot more data collection, that's for sure. As time continues, our understanding of this will improve. But what we see based on various data sets is that Earth's magnetic field strength across 160 million years has historically been quite weak compared to present day value. Here's our present field strength. And so we see that back here around 160 million years ago, these are all the values. And so we see very few of them above this present day line. Most of them are lower. This is our virtual axial dipole moment there. And so you see that we are around this 8 range. It's like 7.75 to 8 or so for our present day value. We have values going well above that here in the modern day. 0 is, modern day. And we see a whole bunch just in recent time. This is 50 million years. Most of them are well below. And so what the research shows is that there is a critical zone that if you go below in field strength, then an excursion is much more likely. Because there's these normal secular variations in Earth's magnetic field, you have these flux bundles that are emerging from the core. It's likely based upon also subduction processes and conductive processes of the mantle. But you have these zones of reverse flux that emerge from the core, or often positive flux that will strengthen the field, emerge from the core, causing these regular rhythms and waves in Earth's magnetic field strength across various locations and across time. But if you go below a certain total axial dipole strength, the main dipole, if that weakens sufficiently, then if those flux bundles emerge like they normally do, that has the potential to then trigger an excursion to occur. And if an excursion stays stuck at that flipped polarity, then it becomes a reversal. So it takes about 2,000, 3,000 years for an excursion to stay there for it to become a reversal based on the geologic evidence. So what happened with Lechamp is that it nearly flipped, but then it started to move back. It didn't stay there for 2,000, 3,000 years. And so the normal polarity that we live in right now returned. But in general, what we see is that the magnetic field strength of Earth has been quite a bit lower than the present day field strength right now. And that's a key component to whether there is a pole flip that is happening at this moment in time. Once again, we have our 800,000 years of magnetic field data here. And so we see this critical value of intensity at and below which excursions occur. And this is about 4 times 10 to the 22 for our VADM. And so we see that below this line there, this is 4, this line is 4. We see that below that line is where we get all these excursions. We have our reversal there, and then we have all the different excursions, and there's Lechamp, and we see that our field has gone up quite a bit. It's well above 4. It's around 7.75 to 8, as I mentioned. So we are well above that apparent critical value. This could just be a correlation, but we do see that anytime the field strength gets in that range, that's when an excursion occurs, that's when a reversal occurs, and it's not a quick process. It doesn't take 10 years. It doesn't take 20 years. It takes hundreds of years for an excursion to occur or for a reversal to occur. It's not a fast process. On the geologic time scale, it may be fast, but on our time scale, it's very, very slow. But you have to get to these critical values, it seems, for that to really be able to happen, because you need the quadrupole magnetic field to overwhelm the axial dipole magnetic field, allowing it to then change its flux and to flip and then re-emerge and re-strengthen in the opposite polarity. Earth's magnetic field isn't made up of just a dipole. It's also made up of higher order components like a quadrupole magnetic field. And so we can see exactly what that looks like with this graphic here. Here we have a quadrupole, and we see how it varies as compared to a dipole. Now, 90% of Earth's magnetic field can be characterized and described by a simple dipole, just like you get with a bar magnet. We have polarity here, polarity there, and you have some field lines that go out, you have other field lines that go in. For example, with Earth, this would be the northern hemisphere, the north magnetic pole. It's actually the south pole. And then here for the southern hemisphere, we have the south magnetic pole. But Earth also has a quadrupole. There are these other higher order expressions of the magnetic field that are just a lot weaker than the dipole. So they don't really express themselves that strongly at the surface. But as the dipole weakens, and we are seeing Earth's magnetic axial dipole weaken, then things like the quadrupoles can start to become more easily expressed at the surface. And we are also seeing an increase in the strength of the quadrupole across time. But the degree of these changes is what's important. And the reason why is that will allow us to understand whether we have an excursion or a reversal coming up. Here we have the Lechamp excursion, the most well-studied excursion going back to 41,000 years ago or so. And we see that the axial dipole dropped precipitously in its strength. This is a log scale. So we see that it reduced by more than 100 times in its strength, whereas the quadrupole field remained. And actually, right at that excursion is when the quadrupole was stronger than the dipole. And they did some calculations on the quadrupole. It still has a protective effect from space weather. We'll look at that. But we see that when the dipole goes down, the quadrupole basically remains the same. There's some other process that's generating this quadrupole. And then the axial dipole is able to flip and then re-strengthen. And this is where we are now. Of course, in this case, it did not flip permanently because this is an excursion. It did not do a reversal. But it's important to understand the dipole and the quadrupole because they are also a very key component to understanding whether we are undergoing some sort of pole flip or excursion or something like that. And so we are seeing the quadrupole strengthen. We are seeing the dipole weaken, but our total strength for the dipole is still very, very high compared to the historic geologic record and average. And so this dipole would have to drop quite a lot more for this quadrupole to become dominant. The quadrupole would have to strengthen more, or this, of course, would just have to drop even more. So we see that there are variations in the quadrupole. And you see also it's much lower on the log scale, right? This is 10x different. This is like a 20x difference between the dipole and the quadrupole. But we would need both of those things to occur. We have them, but not to a sufficient magnitude for us to really be able to confidently say that we have a excursion or pole flip occurring, let's say, this century. That data just simply is not there. Here we have a really fantastic video showing the evolution of Earth's magnetic field from 50,000 years ago to 30,000 years ago. So this encompasses the Lechamp excursion and also the Mono Lake excursion. We see the Lechamp excursion here, the Mono Lake excursion there. And what we'll see up here on this surface map, this is the core mantle boundary map, is that there are South Atlantic Anomaly-like features that show up in the equatorial regions near South America and Africa, and then they go away, and they're not a herald of an excursion or a reversal, at least according to this model. And this model is really good because it also matches up with nucleotide counts, which are produced by cosmic rays and solar radiation. And there were various abnormalities in the nucleotide counts across this time range that weren't explained by just looking at the Lechamp excursion, the Mono Lake excursion. But once they created this model, they saw these other changes in the magnetic field and were able to exactly line them up with those abnormal nucleotide counts. And so this model is likely very accurate. So let's watch this again. I'll pause it where necessary. So here we see a very strong dipole, and we do see a South Atlantic Anomaly-like feature start to form. We saw that earlier right there. And that was about 48,000 years ago. We also see this form right there, another South Atlantic Anomaly-like feature. But then the normal dipole returns. Until then, the excursion occurs about 4,000 years later. And so during the excursion, you see the dipole strength goes down. You have all these kind of random multipolar regions on the core mantle boundary, but the overall axial dipole strength goes way, way down. And then this starts to normalize. And so some of that intense flux that we were seeing goes away. And then as we go towards the Mono Lake, we see this start to become more complex again. We see the overall strength go down again, but it's not as severe as Lechamp. You see some multipolar regions like there, some kind of like outflows like this, but then things return to normal once more after that Mono Lake excursion occurred. And that was quite minor compared to the Lechamp excursion. So we do see these South Atlantic Anomaly-like features evolve with this model. I'm going to pause it one more time. I mean, we kind of see them transiently through this entire range from like 50 to 46,000 years or so. But here's one right there. We see that doing the same thing. It's also drifting westward. Right now, the South Atlantic Anomaly, it formed originally kind of over this Africa area, and it's drifted westward. And that's where its minimum intensity has also drifted as well. And it's expanded in its extent quite a lot. But we see that with this model, it expands, it grows, and then it goes away. And eventually the normal dipole arrangement and the normal equatorial arrangement reappears. Of course, then we had the Lechamp excursion about 4,000 years after that. So what this is generally showing, though, is that the secular variation of Earth's magnetic field is always changing. You have these changes always occurring, whether it's like a South Atlantic Anomaly-like feature, or whether it's a magnetic high zone that forms over Europe, for example. There was a really big magnetic high that formed over Western Europe just about 1,000 years ago. We'll look at that and other regions too. And so we have these waves of activity in Earth's magnetic field because Earth's geodynamo process, or at least its magnetic field creation process, is chaotic in a way that we don't understand. And we're just now starting to see these rhythms of activity as we really develop really good models, and also as we are starting to collect a sheer abundance of archeointensity and paleointensity measurements. And you really just need a bunch of measurements across long periods of time to be able to piece out those lower intensity but higher frequency changes in Earth's magnetic field, those rhythms, because an excursion really stands out. It's a big event. A reversal, you're going to see that on the ocean floor with the polarity change. But these smaller secular variations that take 200 years, 300 years to kind of grow and then subside, those right now are hard to track, and we're starting to find more and more of them. The reason why so many people are focused on a pole flip or a geomagnetic excursion, geomagnetic reversal scenario is because of how it's going to affect our day-to-day life if it were to occur. We're so technologically dependent now. And what we're seeing, for example, with the South Atlantic Anomaly is that outside of the North Pole and the South Pole magnetic field cusp, it is the preferred location for high energetic particles to go ahead and precipitate down to the Earth. It also receives more cosmic rays, which are the most highly vibrational particles that come in from space. And they are routed by magnetic fields, but with the South Atlantic Anomaly, the magnetic field strength is weak, and so there's a higher radiation load there. And this can cause problems with satellites. It also means that during a geomagnetic storm, the geomagnetically induced currents are stronger. These flow along wires, can blow out a substation, for example, cause a power outage and bring about other technological failures. And so if there was an excursion or reversal to occur and the field strength was to drop, how would that affect our technology? There's also some people that have linked these sort of excursion or reversal events to mass extinctions. Though that data is by no means agreed upon, there may be a link there, how it affects life on our planet. And so we see here some different modeling that they did for the solar wind on the Earth under different circumstances. Here we have our normal axial dipole, and we see the magnetopause is quite far out, and we have solar wind coming in at the poles. Here is a quadrupole. The axial dipole in this instance has, greatly reduced in strength. And so now we have this quadrupole arrangement. We still have some energy coming in at the poles like normal, but now we also have this area with the equator. We see that the magnetopause is much closer in at about 3 Earth radii instead of like normal 5 or 10. It depends on the space weather. And then here we have a mixed arrangement where we have one of these magnetic lobes larger than the other, and it's also a different scenario, but still the magnetopause is pushing very close. And they're specifically looking at how this would affect Earth's atmosphere and atmospheric loss, but it also speaks to how space weather effects would be stronger with a weaker magnetic field, especially one that's undergoing some sort of excursion or reversal. The space weather effects will be extreme, but we've gone through them many times, and there doesn't seem to be the strongest match between like mass extinctions and reversals. I don't think life would survive if there was, though maybe there is some evolutionary selective pressure that exists. Now, this is what's happening right now. And to show you once more, here's the dipole field. This is a great graphic. Here we have the quadrupole field, and here we have the octupole field. And we also have this. This is a higher order mode of Earth's magnetic field, but it's a very small components, percentages, so it's very tiny. 90% of Earth's magnetic field can be explained with a dipole. But here we have our dipole field in blue. We see that's been going down in strength, and we have our non-dipole field, which is made up of all the other components, going from 3 to 6, I believe. From 2 to 6. You can see that right there. The non-dipole field is given by the harmonic contributions from 2 to 6. In red, increasing in strength. Now, if you were just to look at this, you might get alarmed because you see that this blue has gone down just as much as the red has gone up, and you think that actually now the non-dipole field is stronger. But look at the scaling here. So this is our power spectra, 10 to the 7 here for our non-dipole field, 10 to the 9 here for our dipole field. So they're in different scales, and they're also at different levels there. This is 2.2, 2.15, goes down to 1.75 at the bottom. But here are the bigger jumps. It's going from 5, 7, 9, all the way up to 13. And so there is this increase in the non-dipole field. There is this decrease in the dipole field going from 1840 to now, and actually goes further back. It goes back to about 750 CE, where we've been seeing this trend continuously, that negative 12.5 nanotesla drop per year, 5% per century. But it's also, the dipole field strength is still very, very large and within the normal range of secular variation. And there's a lot of geophysicists that think that's about to actually re-strengthen or at least level out, because we're at this range where historically, geologically, that's what does occur. We have these ups and downs, and then it just kind of reestablishes equilibrium because the wave now is bottomed out and it's about to go back up. But yes, we are right now having our non-dipole field strengthen globally and our dipole field weaken. And we're seeing that express itself through the South Atlantic Anomaly, where some of that flux coming out from the core, at the core mantle boundary, is reverse flux. It has the opposite polarity, so it's subtracting from the strength. And as it merges out, it's going to create that. Now, if you remember back to the Champs slide where we showed that South Atlantic Anomaly form multiple times in that model, one of the reasons why is there is this low velocity shear wave zone along the core mantle boundary underneath Africa and the South Atlantic area. That zone has this anomalous low shear wave velocity zone. This is a known thing. It's based on the geology, some different factor in the mantle, or maybe some subducted slab. If it's a low shear wave velocity, then there's more liquid there. It's more fluid. Shear waves don't travel through fluids. And so that could be responsible for the South Atlantic anomaly, or at least a big modulator of it, because if it's this different geologic feature, then it could modify the flux coming out of the core in such a way that it reduces the field strength. We also have new studies that came out showing that there are these protoplanetary slabs underneath Earth's crust still from the impact with Theia. And so there are a lot of unknowns in our mantle and around our core with our core that all determine Earth's magnetic field strength, because it dissipates through the mantle and through the crust until it reaches the surface by more than 99%. The magnetic field strength at the core is 99% stronger or so than it is at the surface. So magnetohydrodynamics and how magnetic fields push through the mantle is very important to understanding what's going to happen, and that's really the bigger factor at play here. It's not like these changes from the core are instantly expressed at the surface. There is this evolutionary process, and it seems that there's these blobs of flux that either are positive or negative that get pushed out, slowly emerging through the mantle across hundreds of years, and then expressing themselves at the surface across hundreds of years before eventually it just fully gets pushed out of the Earth and things return to normal before the next one occurs, or there's multiple of these happening simultaneously. And that seems to be what is the case. A really important component to all this that I touched on earlier is the distribution of our data. Because if we don't have good data distribution, then our models aren't going to be as accurate as they could be. There could be some glaring inaccuracies, in fact. And so, as it relates to Earth's magnetic field, the stronger the change in the magnetic field, the stronger the secular variation across space and across time, the more likely that is to be captured in, let's say, a lava flow, or to be captured in someone creating a pot and making some sort of clay vessel out of it. They fire it in the kiln, they record that remnant magnetization, and then we dig up the sherd later. But if you don't have that strong of an excursion, for example, then you're going to have less data available to understand how it even occurred, or even to find it in the first place. And so what we see is that Lechamp was very strong of an excursion, the strongest in recent time, because we have all these data points. And we have good distribution on them. I mean, we could wish for more in South America there. We could wish for more in Africa. There's none in Australia. But we do have good distribution in general with these points there in the ocean. But you do see in general more distribution in the northern hemisphere. There's more land there, there's more people there. 90% of people live in the northern hemisphere. More research is done there. And so in general, there's also this bias away from the southern hemisphere in general, which skews our data. And so we only have the swarm satellites now and other magnetic field observatories around the surface up in the ionosphere collecting these measurements now that aren't biased in terms of which hemisphere. They just circle the globe continuously. But back with the relative intensity measurements, when Gauss invented the absolute intensity measurements, all those were heavily skewed towards the northern hemisphere, and that influences all the models that you see of Earth's magnetic field strength and evolution across time. Going back to 1840, before that, all that stuff is heavily skewed as a result of that. Doesn't mean it's inaccurate, but that's important to keep in mind. Other reversals or other excursions here, we see closer in time there, further back in time at Mono Lake, and then even going back further than the Lechamp excursion at the Norwegian Greenland Sea, post-Blake, and we see not that many data points are registered. So this is really important. We want good data coverage and distribution to really assess what happened and the secular variations that occurred. And there are highly local features that sometimes do emerge. We're about to look at those. But big events require big evidence, and they create a lot of evidence across the entire globe. And so Lechamp was the main excursion that occurred back in the day. We see all the different evidence here for that as well. And you see some others there. And as you go further back in time, the data record and the resolution just gets lower and lower and lower. And so we don't have those records of the temporal evolution and the secular variations across time for Earth's magnetic field, painting this picture that it's normally static. But in fact, it's quite dynamic because that core process is chaotic at its core. Here we have another slide showing the importance of data distribution as it relates to our ability to understand these secular variations of Earth's magnetic field, which, as you remember, is the most important component of understanding where Earth's magnetic field is going. If we understand past secular variations across space and time, we can better understand how it will evolve in the future. And so this is for 3 different age ranges here: the Gauss era from about 1840 to 2009. We have 1590 to 2009, then also going all the way back to 0 AD, 0 CE, Common Era, to 2009. And so we see that the Gauss era has the least amount of data because it's the smallest time frame, and that slightly expands. They also applied a filter to their archaeointensity data. These are like remnant magnetization signatures stored in pottery sherds. So during that firing process in the kiln, they record the magnetic intensity, and then they can retrieve that using special techniques. And so you see that they filtered out a whole bunch of data here. They had all this in gray, they only took the red. But if we look at our maps, we see a extreme lack of data in the southern hemisphere once more. And this isn't just for the Gauss era, it's also for this longer time frame there, going to 1590 and also going all the way back to 0 CE. So we have just a little bit of data in Africa, just a little bit in Australia, none down here, very few in the oceans in general. There's Hawaii, right? And also look, not that much in Canada, way up north. Polar bears, it's dangerous, it's cold often. And so we see that our data distribution could be much better. And so we're creating these models off of really highly localized data groups here, a little bit there, some in Asia, but in general, it's very, very non-homogeneous. And so it's really important to keep in mind because all these data are based off of that. Right now, when we look at Earth's magnetic field, we see the South Atlantic Anomaly, and it's this really big area of low magnetic field strength. And it's the main anomaly that we see on Earth's magnetic field. The bifurcation of the North Pole into the Canadian lobe and the Siberian lobe is also interesting, causing the movement of the North Magnetic Pole from Canada to Siberia. But really, it's the South Atlantic Anomaly that's the big variation right now in Earth's global magnetic field. And that's really the variation that's having people look at the possibility of an excursion or reversal occurring in the near future. We do see, though, in our recent past, other variations in Earth's magnetic field strength that are just as significant, but almost all of them were in the opposite direction. They were all field strength increases. So here we have full vector geomagnetic variations at Hawaii for the past 1800 years. And Hawaii is a great place for this because it's a shield volcano and it's constantly having these new volcanic flows. So they finally went out there and collected all these different data sets from different flows, and they were able to create this pretty nice graphic showing this anomalous intensity bump going nearly to 70 microtesla. So right now at Hawaii, the field strength is about 40,000 nanotesla, a little bit lower, things like 39 or so, somewhere in that range. But back just 1,000 years ago, the total field strength intensity at Hawaii was about 68,000 nanotesla, or here 68 microtesla, or that'd be 0.65 to 0.68 Gauss. And so this shows you that there can be rapid swings in Earth's magnetic field strength, down or up across time. And this is a pretty short blip. This is maybe if you were to go from here to there, like 200-300 years. So it's a pretty short-term variation. We also have new archaeointensity data out of France that goes back about 1,600 years in high resolution based on archaeointensity pottery sherd data. So here we can see the type of pots that they are using. They find these old pots, they're well dated to certain time ranges, and then they'll take some of these sherds and they'll process them and they'll record that intensity data from them. Here's the distribution. They have 2 different radii here, one at 700 kilometers, one at 1,250 kilometers to create their total magnetic field strength changes across time. And so we have now a look at the total magnetic field strength of France going back to near the turn of our epoch, going back to 0 AD. Let's give it a look. And here's what they found. We see that Earth's magnetic field strength was quite a bit higher back around 600 to 800 AD, and then it started to go down. But you also notice this interesting wave pattern there. So there is this secular variation that has a frequency of about 256 years that's superimposed upon the larger trend. But we see that the field strength there, the intensity in Paris, microtesla is 60, so 60,000 nanotesla, went all the way up to about 80, and now it's in this about 50,000 nanotesla range. We see that the strength has actually been increasing there for a while. And if you look at the data out of Edinburgh, since they began recording absolute intensity measurements, the magnetic field strength in Edinburgh has also gone up slightly. So it's not decreasing in strength uniformly around the world. They have different models here, one with the data set 700 kilometers, 1,250 kilometers, and then selected data. But they all in general show the same thing. They show this really big anomalous increase in the magnetic field strength around 600 to 800 AD in Paris in France, and then a decline there with these other secular variations, these other normal rhythms superimposed upon it. If we go back here, we can see the power spectral density plot for that time period, and we see this clear peak there at 256 years. And this is that wave cycle that they found in Earth's magnetic field strength, the intensity. So this purple line there is correlated with these bumps. Of course, there are larger trends at play, so it doesn't show up and pronounce as much as this purple line is, but we do see these waves manifest upon the larger trend, altering Earth's magnetic field strength across time. So this really nicely shows the different frequency secular variations that Earth's magnetic field has. We also saw a very large anomalous increase in Earth's magnetic field strength in and around Israel near the same time frame. So here we have this data graphic, large geomagnetic field anomalies revealed in Bronze to Iron Age archaeomagnetic data from Tel Megiddo and Tel Hazor, Israel. These are different settlements that existed for a very long time. So we see our range there, right, in Israel, but also just in general, this region, the Middle East. And there's a lot of different data sets collected across this region, Syria, Turkey, Israel, a lot more countries in this zone that show a similar intensity high at the same time frame. So this is very good data that they have out of the Middle East in regards to this. They're investigating it for some reason. Clearly it's interesting, it's an anomaly. Here we have 3,500 BCE and then going all the way to 0 CE or AD. And so we see Earth's magnetic field strength had a slight bump there in this in this 2,500 to 2,000 BCE range. But then it had this really large double spike in the magnetic field strength at around 1,000 to about 600 CE. And it's really quite significant. Let's zoom in on that. Here we see that double spike, and what I want you to notice is the virtual axial dipole moment there is 100. Here at the top it goes nearly to 200, so it's almost a doubling of the intensity of the magnetic field for this region for this time frame. We see that first one starting just after 1000 BCE. We see the second spike there, maybe around 700 BCE if we keep the numbers very simple. But this very big anomalous spike showing some sort of magnetic flux bundle getting pushed out that was increasing the magnetic field strength in the Middle East at that time frame, and then it went back down to its normal variation there. So it goes to show you and really demonstrates nicely how Earth's magnetic field has these different rhythms to it that have different time frequencies and like scales and intensities to them, and they're all overlapping together, and that's what makes this whole process chaotic. If we go back, I also want you to notice that the virtual axial dipole moment is quite a bit lower for the past than it is recently. So here it's all the way down to like 60 or so, and this stops at 0 CE, but we see that there was this general increase in uptrend during this time frame. And so these low values are not anomalous because we did not have an excursion back then, right? We did not have an excursion or a reversal of Earth's magnetic field at 4000 BCE, but the field strength was lower then than it is now. And that is one of the most important components for determining, as we discussed, whether an excursion or a reversal will occur is that total axial dipole magnetic field strength. It has to diminish sufficiently for that quadrupole to be stronger. And so even here in this regime that was quite low in strength, we did not have an excursion or a reversal. And so what we're seeing now, we are seeing the growth of the South Atlantic Anomaly, which has some people looking at whether this is a foretelling of an excursion or a reversal. We are seeing changes with the North Magnetic Pole, moving flux lobes, and in terms of the average rate of reversals, we are overdue, though that average is just taking all the dates and averaging them. It's not, there's really no rhythm or trend to it. It's not like an earthquake reoccurrence interval, which generally has some sort of trend. It's the magnetic field strength is one of the most important determiners of whether an excursion or a reversal will occur based on the best geologic and geophysical research and data that we've done thus far. If we take some of these recently discovered secular variations of Earth's magnetic field strength for the past 2,000 years and put them into a graphic, this is what we get. We get these intensity curves going from 400 to 2000 AD for different locations. So here in dark blue, that is Western Europe. In light blue, it's France. They're the same location, basically. We have here in red, Hawaii. Yellow is Japan, and green is Mesoamerica, which if you look here is effectively California. And so what we see is that they were in general grouped up higher in this virtual axial dipole moment zone. The magnetic field strength was higher for all these locations, but then they all had variations that were increasing the magnetic field strength. So France and Western Europe in general saw this bump there around 800 or so AD. Then Hawaii saw it around 1000 AD. And Mesoamerica saw this big jump around 1500. So just recently, we saw this really big increase in the magnetic field strength in the west coast of the US and also down into Mexico. And we see that going all the way up near 150, 160 for the virtual axial dipole moment. And we also see that dipole moment there plotted in gray, and we see that they all started to kind of confine to this downtrend that we are in, this weakening of the field strength. But back here, it was less apparent. There was a lot more variability. So there was a lot more variability in Earth's magnetic field across the globe in terms of its strength back at the last millennium. So around 0 AD through 1000 AD and even into 1500 AD. And this is all recent time. This goes to show that there are always these variations. And yes, things are now a little bit more constrained, but they were also constrained. For example, here it was just Mesoamerica that seemed to have underwent this anomalous magnetic high, this flux bundle perhaps that was pushed out from the core, modulated maybe by subduction processes. We see here the subduction zone, the subduction zone up here, but then the transform fault zone there. And we have that South Atlantic Anomaly near the mid-ocean ridge spreading center in the Atlantic Ocean, also the subduction zone off the coast of South America, the west coast. And so all those processes too, like the subduction of ocean slabs, is perhaps modifying the magnetic field expression at the surface and in space, the magnetosphere as a whole, because they're altering the magnetohydrodynamics. And we see that with that low shear wave velocity zone at the core mantle boundary under Africa. We also don't see any secular variations in Earth's magnetic field strength over the Pacific Ocean, which is a very large plate that has very little changes to it. It's not one of these tiny little plates like in Israel and the Middle East. There are a whole bunch of plates that meet there. So there's a lot of interesting things that are occurring. We know earthquakes are linked, they have electromagnetic components to them, for example. But the Pacific plate is this really large plate that undergoes very little changes. Of course, the ring of fire is around it. It does have a spreading center kind of off to the far southern hemisphere, but we see very few magnetic field secular changes over the Pacific Ocean. So this is linked to processes that are still being learned about, and we're still even discovering what creates Earth's magnetic field in the first place. Here we have our South Atlantic Anomaly and how NASA sees it evolving from 2015 to 2025. And so we see the changes at the surface. We also see the changes at the core mantle boundary. And so we see that there is this flux that's being pushed out in this zone there. It's getting more condensed there. And in general, we see on the core mantle boundary a lot of these different flux lobes. There's not a clear dipolarity at the core mantle boundary. It's much more multipolar. And so some of that does get expressed at the surface if it's especially strong. We have our intensity here. Here we see low intensity, high intensity at the core mantle boundary, and we see this expansion of the South Atlantic Anomaly. And so they have this running from 2015 to 2025. This was created in 2020, so 5 years of observational data, 5 years of forward modeling. And we see how the South Atlantic Anomaly, these contour lines, will actually split and create a second zone there. So here we see the creation of that second contour line there off the southern coast of Africa. And just in general, this South Atlantic Anomaly is the main large-scale secular variation that we're seeing on Earth, though as we touched on with the data showing the Lechamp and the Mono Lake excursions, this could be a feature that appears regularly based on what's happening at the core mantle boundary and as it interacts with certain geologic structures in the deep mantle. And so as the core mantle boundary and the magnetic flux at the core changes, perhaps the South Atlantic Anomaly appears and then disappears. And we get these magnetic highs that appear in the northern hemisphere and then they disappear. And this could be a regular rhythm that occurs. I'm sure at some point someone's going to take all this and compile it into a single kind of cohesive hypothesis or theory. But this is all data that's come out recently, and there were some citations between them. But in general, people seem to kind of be in their own lane in regards to understanding the secular variations and evolution of Earth's magnetic field. Some people are just studying the magnetic field as it evolved in Hawaii, just studying as it was in Paris, for example. But we're starting to have better understandings of how it changes across time. And the South Atlantic Anomaly is very important as it relates to understanding whether we are in a geomagnetic excursion or reversal, the very beginning. If we are in one, which we can't say we are or we aren't. If we are in a geomagnetic excursion or reversal, we're in the very, very beginning. The North Magnetic Pole is still way up there in the northern hemisphere. We would need that to start tracking through the mid-latitudes and then actually past the equator for it to really be like, oh yeah, we're in an excursion, right? So any absolutist claims that we are in one now are doing a disservice because we don't have those key characteristics in front of us yet. The magnetic field strength is still very high compared to historic records, compared to the absolute minimum needed for those excursions to get triggered. Us being past our average reversal date really doesn't mean much when there's so much difference in frequency in when reversals occur. And sometimes we can have polarity that lasts the same for millions of years, not just 780,000 years. And the South Atlantic Anomaly could be a transient secular feature on the timescale of hundreds of years rather than something that is imminent of an excursion or reversal to occur. But it is important to understand, and we're better understanding it now with all the available data that we have, the geophysical observatories and more. There it is, my video on Earth's magnetic field strength, where it is right now, where it was in the past, and where it may be going. Is Earth's magnetic field weakening? Yes, it is. Is it at a critical threshold for an excursion to occur? Probably not. We're still quite a bit stronger in our total magnetic field strength than that absolute minimum intensity needed for an excursion to occur or a reversal to occur. So while it's too early to say, it's also too early to say. Anyone that's absolutely saying that there is some sort of excursion or flip that's occurring right now is just as much, in my opinion, in the wrong as someone saying that there's zero chance of one occurring. But there's a lot more data as I see it, and decide of these are normal secular variations and there's nothing to be worried about. We do see increases in the South Atlantic Anomaly, but that is something that we've also seen across other periods of geologic time, just in the other direction with these increases. And so it really all comes down to what's happening at the core and how is that magnetic flux moving through the Earth. And we look at the sun and we see how these bundles of flux during the solar flip, during solar maximum, how they move through the sun, creating these sunspots. On the Earth, it occurs over a much slower time scale, but the physics is likely very similar. And so this South Atlantic anomaly could just be a bundle of reverse flux that's moving through, and eventually it'll just dissipate out, and then the field strength will return to normal in that region. And there could be another zone of higher flux, positive, that's going through in a different zone that soon will make itself manifest. For example, like with Edinburgh, Scotland, the magnetic field strength has slightly increased over the past 150 years, whereas the total strength for the globe has dropped 12.5 nanotesla per year. 5% per century, the total field strength dropped by about 10 to 12%, not 20, not 30, not 50. Those are simply incorrect. You can look at the data yourself going to intermagnet.org. I highly recommend you do that. They have all the different global magnetic observatories available for you to research and look at. And if you'd like to learn more about Earth's magnetic field, if this wasn't enough to satiate you, I have a 2-hour-long master guide on Earth's magnetic field that goes much more in depth on all the other topics too, like georeactor and geodynamo theory. I go out into the plazosphere. We talk about geomagnetic storms, things like power line harmonic resonance, which is an increasing phenomenon of importance and significance now in our modern technological day and age. We also talk about excursions and reversals in depth, so I highly recommend you check that out. I'll put a link in the video description. Or if you sign up as a special channel member at the superstar level, you get access to that on YouTube directly, ad-free. It's a 2-hour lecture, and this is really the next step, the next place to go after this video if you want to learn more. So again, thank you. I've been your host, Stefan. Welcome to the channel if this is your first time here. Like the video, help this channel grow. Please subscribe. I hope to see you around, and I'll see you all in the next video.